So we're in 3.6 and we're just going to close this up by going over the takeaways. Takeaways are a good place for you to kind of like remind yourself what we were supposed to learn and just like clean it all up, clean up all the understanding. So some true statements about number operations, and I'm just going to annotate right on top of, yeah, this is 3.6, exactly. Yeah, I'm going back because I need to finish this up. So I'm just going to annotate right on top of here. You can annotate wherever you want. You can write this on a notepad. I definitely suggest that you put this somewhere. So the first thing that I want to say is I want to note it says some true statements about operations on numbers. Some true statements on operations of numbers. Hold on a second. Okay. What is this talking about? Hold on. So we are talking about complex numbers, right? So we had made a bunch of claims towards those other numbers. The sum of a rational number and an irrational number. Hold on a second. Let me get to grab this right here. So remember we were talking, wait, hold on a second. Let's go students. Remember we had made these kind of like the sum of an irrational number and an irrational number. So we want to close these up and we're going to type these out just so that we are all on the same page and everybody knows what is true. Okay. So, all right, let's see. Let's see if you guys remember the sum of a rational number and an irrational number is always, sometimes, or never irrational. What do you think? Yeah, it's always irrational. Always irrational. Always irrational. Okay. And why is that? Well, you guys said it over here. If we think about, where is that one? I don't think it's that one. Yeah, it's this one. So if we add a rational number to an irrational number, it'll always be irrational because you can't get rid of this irrational part, right? Very good. Okay, let's go back over here. What about if I subtract? Let me do this in a different color just so it stands out. What about the difference? So the difference of two rationals. What do you guys think? Always, sometimes, or never rational? So here they're really saying, hey, fraction minus fraction, is it always going to be a fraction? Can it always be written as a fraction? Yeah, right. Yes, it always is. So a fraction plus a fraction is a fraction. So the difference of two rationals is always rational. And I'm kind of cutting the words out a little bit just so we can get through this. Okay. It's not a different color. That's so funny. Let's try a different color. Here, here. Okay. So here. Yay, it's a different color. Okay, so what about if I multiply, so product of two integers? Okay, remember what an integer is. An integer is a positive or negative whole number, right? So think about all the numbers on the number line. So let's say a -2 times a +4, is it always going to give me an integer? Always, sometimes, or never? Yeah, it's always. Wait, product of two integers, always integer. Yeah, Miss Johnson's missing a couple of keywords, but you guys all get what I'm saying, right? And the reason why is because if you think about, let's see, let's go back over here, Miss Johnson. if you think about this picture, I really want you to be able to use this picture. Ignore all my writing. It's just layered on top. If I'm here in integer land, right? If I'm here in integer land, what's not in integer land? Well, rational numbers are not. So fractions. So how do you get to fractions? Anybody know how you would, when did you start learning fractions? After you learned what operation? When did you start learning about fractions? After you learned about what operation will get you a fraction? I'll say it like that. What operation? Yeah, it's division. Very good. So notice here, our question was the product. You told me dividing will get me out of integers. So multiplying will keep me in integers? Yes. So when I teach this senior math class called MRWC, and I love it. And one of the things that we really go over is these number sets and how to get in and out of them. Well, if you think about it, how do you get from whole numbers to integers? What operation did you introduce that now you all of a sudden had negative numbers? What operation was that? Yeah, subtraction. Now, why? Because a positive number, like say 3, and you subtract off a bigger number, like 10, all of a sudden now you're kicked into negative land, right? So I really like when you guys think about these big ideas, because that takes you out of like the boring part of math and into the more interesting parts of math. I know some of you are like, Ms. Johnson, all of math is boring. No, it's not. It's actually pretty dang interesting. Okay, I'll stop. Okay, what about if I multiplied two fractions? What if I multiplied two fractions? What if I multiplied? So product of two rational numbers. Okay, so think about it. Fraction times fraction. Fraction times fraction. Always, sometimes, never. Fraction times fraction. Always, sometimes, or never. Is it always a fraction? When I multiply two fractions. Okay, so then I'm going to bring you back to this picture again, right? How do you get out of the rationals? So if you're not in this box in the rationals, you're over here in irrational, right? Or you're out here in complex. So an irrational number looks like the square root of 3. Do you guys remember that? And over here, imaginary is when you have the square root of -5. Right? So you're like, okay, well, what, Ms. Johnson, what do you want us to do? Okay, well, I'm asking if I multiply, because this is the one we're on, if I multiply two fractions, will I get a square root? Will I get a square root of a negative number? Yeah, it's no. So therefore, the product, right? The product of two rational numbers is what? Always, sometimes, or never. Very good. Always rational. Yeah, I can't kick myself out of rational until I start doing what operation? What operation is going to kick me out of rationals? What operation do you see here? Yeah, square rooting. Very good. Very good. Very good. Okay. Moving on. Sorry, I need to go back over here. I'm going to keep this slide here because I like it. What about the product of two real numbers? So if you're not real, then you're imaginary, right? If you're not real, then you're imaginary. Perfect. Thank you for telling me. That's funny. Okay. Okay. So here, so if I have a real, am I multiplying? Yes. So product of two reals, product of two real. Is that going to kick me out to imaginaries? Everyone says no, right? So this is always real. Very good. Very good. So Ms. Johnson, what is the whole point of this? The whole point of this, oh, last one, complex numbers, last one, complex. So product of complex is always complex. Ms. Johnson, what's the point of this? The point of this is called closure. It's this word called closure. So I'm going to keep this up here. I'm just going to move slides. It's not going to take any of my writing away. But the point of this is closure. So can you guys all imagine? I'm going to scoot all these things to the side here just so that we can read what this slide says. So, oops, these two were two parts. Okay, and okay. So it says a set is closed under an operation if and only if the operation on two elements of the set produces another element of the set. These words are really confusing. I'm going to explain closure. Ready? A rabbit and a rabbit, when they get together, yeah, we're talking about rabbit sex right now. I know, it's just kind of crazy. So if I have two rabbits and they get together, what kind of babies are they going to have? Are you guys still shocked that I said sex? I'm so sorry. Are we over this? Are we over this? Okay, good. Okay, we're over the shock. Okay. You guys are, yes, very good. Thanks for bringing me back. Always my buddy Robert bringing me back. Okay, so yes, a rabbit, when they mate with another rabbit, you get rabbit babies. They're called bunnies. It's amazing. Yes, bunny babies. Exactly. Okay. So they're basically asking you the same thing, except for now we're talking about numbers. You guys are like, Ms. Johnson, are you saying that numbers have sex? No, numbers do not have sex. Numbers operate on each other, right? They add, they subtract, they multiply, they divide. And the result of that is what I'm talking about. I want to know what their babies are. Okay. You guys are still on sex. Oh my God. Okay. So a set is closed under an operation if and only if the operation, so bunnies is closed under sex. That's what we're saying. Because when you take two bunnies, it produces another bunny. Okay. So same thing goes here. The product of two integers is always integers. So integers are closed under multiplication. Okay. So 5 and 2 are natural numbers. So therefore, natural numbers are closed under addition. Okay, they're closed under addition because natural number plus natural number makes a natural number baby. Is that okay? I know you guys are still like, but it is not closed under subtraction because look, 2 and a 5 do not make a natural number when you subtract it. Therefore, the natural numbers are not closed under subtraction. Does that make sense? They're not closed under subtraction. Okay, so closure just means if I take two things from the same set under a specific operation, does it produce more people from that set? So let's do more. So if I take a cat and a cat, so like that means that number is not, oh God, sorry. Okay, so if I take a cat and I take a cat, when they mate, or is it going to make more cats? And everyone says, yes, Ms. Johnson, it's a litter class. So cats, the set of cats is closed under cat mating. I know you guys are still on sex. Okay. Sorry. This is one of the easiest ways that I've explained and people get it really quickly. So closure, when we say closure, we just want to know if the babies, if the result is in the same set as the mommy and daddy numbers. So under addition, natural numbers is closed. Under subtraction, it is not closed. So you guys found a couple of different ways here. So I'm just going to leave these up here. So that's our takeaways. So closure, you should all be good on closure now. You're welcome. You're welcome for that great analogy, right?